All right, hi everyone. So hopefully everyone, I'm assuming everyone can still hear me. So let me know if you can't. So thank you for tuning in today. As I said, today's lecture is going to be entirely online today because I'm out of town. But we are going to finish up the module on vector calculus today. And we are going to be talking about line integrals. Last time we talked about surface integrals, and today we're going to be talking about line integrals and Stokes Theorem. So before we do that, Cassandra had mentioned that can you turn in the homeworks electronically? Initially, I would prefer that if you can turn it in hard copy, but if that's not possible, I enabled it in Blackboard so that you can do a file upload, not Blackboard, in Canvas, I'm sorry. If you go to Canvas, you can upload your homework as an electronic file, and then I will have the grader download them and then do the grading. It will be due at 12 p.m. by tomorrow. 12 p.m. and the grader will mark it late if it's turned in after that. The reason I want to have everything turned in by then is because I want to post the solutions so that you have the solutions to study for your exam. I also will be posting just a study guide for the exam, and so that you'll have that. And I would like you to use that study guide to study over the weekend. And whatever questions you have on the exam, we can go over Monday in class. Even today, we can also go over any homework questions, any issues that you have in the homework that you'd like to go over together. Okay, so let's get started then. I'm going to share my screen here. Okay, actually, I need to. I'm going to share the entire screen so that you can see. Okay. All right. Let me know if you all can see my screen. Thumbs up. Okay, great. All right, let's get right to it then. Okay, last module today, last part of the module, line integrals. We talked about surface integrals last time, so let's quickly go over that, and then we'll get right into the line integrals and finish up this module. What I'm going to do is what I normally do is I'm going to periodically check back to the public chat for any questions. After I go through a slide, I'll check back every few slides. So please put your questions on there. And if you'd like your question answered right away, please also, you can feel free to blurt out the question, just to make sure that your mic is on so that I can hear you. Okay? All right. So we talked about surface integrals last time. We'll talk about line integrals now. Let's talk, what are these types of integrals? Well, we have, there's various types of, we talked about integrals on scalar fields. And scalar functions, as you know, they're just numeric. Vector fields have a magnitude and a direction at every single point, whereas scalar fields just have a scalar value at every single point. So we talked about how to do integrals, single, double, and triple integrals with scalar fields. Now we're talking about how to do integrals in vector fields. And the trick is, as we found out last time, is a vector integral really is just an extra step that you have to do to convert it into a scalar integral. So we took the example of the surface integrals that we did last time. We have a vector field A, and we take the dot product of A with this a vector which represents the differential surface area. So that's why it's called ds. Okay, when you take the dot product of two vector quantities, you get a scalar field, and then you just integrate that scalar field over two dimensions in the case of a surface integral. What we're going to be doing today is we are going to be doing a line integral where we integrate over a line. And in that case, you also see that there's a dot product here, the vector field here. It's dotted with a differential length, a vector that represents a differential length along the line. But you can see that in this case, it's also a vector. So that in both cases, the dot product of the vector field with the differential surface or the differential length, they both result in scalar quantities. So these things are just one extra step that you have to do to first convert that vector field into a scalar quantity, and then you can just do the integral normally. All right, there's a few additional things that we have to keep in mind when we do that, so we'll go over that. All right, just really quickly, we talked about tangential and normal components of a vector on a surface. I'm not going to go over that today because we talked about that a lot last time. We did some examples of that. We talked about surface integrals. The idea of a surface integral is that you have a two-dimensional surface and you have a vector field. And what you're doing is you are looking at a surface integral is giving you the flux of the vector field through the surface. So you can see these blue arrows here, and you can see that some portion of those blue arrows are going through the surface that you see here that's in red. All right, when we do a surface integral, we are calculating the outward flux from the surface. All right, we talked about what the surface integral is, what it physically means, and then we talked about the divergence theorem. And the divergence theorem said there's actually two ways that you can calculate the net outward flux from a surface. One way is to do the surface integral, as we just talked about, and that requires you to integrate the field vectors over a surface, and that surface has to be, if the surface is closed, you can use the divergence theorem as a shortcut to find out what the net outward flux from the surface is. So we take this example of a sphere, okay, and the net outward flux from the sphere is the sum of all the arrows pointing out of the sphere. In this case, it's the electric field from a single point charge. Another way that you can solve this problem is that you can take the integral of the divergence of the vector field, and that will also give you the net outward flux. Okay, and we did an example of that in cylindrical coordinates, and we found that the net outward flux from the surface was 2 pi. And then this other example that I showed you in class is, we did not do it in class, but here's the solution. And I think that you should do this in preparation for your exam, because you'll probably have a question like this example or like the previous example. You will definitely have a question on the divergence theorem on next week's exam. All right, so now we talked about line integrals. We'll focus more on this today. All right, again, the difference between a vector field integral and a scalar integral is shown here. This is the typical integrals that you do and that you've done in your calculus courses. When you take the integral, what you're essentially doing is you are finding the area under the curve. All right, you're trying to find the area under this whole curve here like this. All right, and the strategy for doing that, what the integral does is that you look at each point on the line, as you see here. You look at each individual point, as you see in the red here, and you multiply that by a differential length along your x-axis, and then you multiply that differential length by what f of x is, so the height here. So essentially, what you're doing is you're measuring the area, you're getting the area of this rectangle. And when you integrate, you're essentially you're summing up the areas of those integrals. It's called a Riemann sum, to find the area under the curve. Okay? When we do line integrals, instead of working with a one-dimensional function like this, you work with a vector field, which could be 1 dimension, 2 dimensions, 3 dimensions, what have you. But you're going to multiply, you're going to take the dot product of that vector field along the differential length vector that's along a line. So what this physically represents when you take a line integral is you are looking at how the vector field is acting on this line that you have drawn. Okay, so the line example here is just shown in green. There's no equation for it. It's just an arbitrary line like this. What the line integral will tell you specifically is if this line represented an object that was placed in a force field described by the vector field A, the line integral would tell you the tendency of this object to rotate. Okay. Now, why is that? So let's look a little bit more closely at this. So the line integral is taking a dot dl at every single point. So if we were to look at this example here, we're at this point shown in the red dot here. Okay, so the vector field is pointing in the upwards direction, and so the vector field is pointing in the upwards direction, and some component of that vector field is pointed in tangent along this line. So what we're doing here is by taking the dot product of a dot dl, we are taking the component, so a dot dl is the component of a along the tangent of the line. Okay, so you imagine that the vector field A is pointing in this direction. I'll draw this in a different color here. All right, draw it in blue. So imagine that this vector field is pointing in this direction here, like so. All right, some component of that vector field is going to be along this vector dl. Okay, well, by looking at the line integral, what we're doing, I'll draw this in a different color here, is we are taking the component of that vector along dl. All right, so this is a dot dl. That's physically what a dot dl is. Now let me make this a little bit bigger so you all can see. So this is your vector A, that's your vector field, and we are taking the component of A in this dl direction, and dl always points tangent to the line that you are looking at. Okay, and it points tangent to the line in the counterclockwise direction. So if I were to take another example here, so I'll draw the vector field A again. So at this point, A is pointing in this direction. All right, now if we were to take the component of A along dl, so first of all, like this is A, the red line is dl. Notice that dl is pointing tangent to the line in the counterclockwise direction, and we are going to take the component of A along dl. And that component you're going to see is going to be quite small because they're almost perpendicular to each other in this particular position. So the component here would look something like this. And you can see the component here, the vector a dot dl, which is shown here, a dot dl is that tiny vector there. Okay, so this is A pointing in the upwards direction. This is dl, the red one, pointing in the tangent to the line, the green line. And then A dot dl is the vector, the component of A along the red line. So it's the length of this vector right here. That's what the component is. All right, so that's what the physical meaning of A dot dl. So when you finish taking the line integral, you sum up the A dot dl's all the way around this line. What it'll physically tell you is the tendency of this object that you have drawn, the tendency of that object to circulate. So the tendency of the object to rotate if the force field was, if the vector field represented some kind of force on this object. Okay, so this is a clear difference from the divergence. The divergence represents the net outward flux going through a surface, and this one represents, you draw a line here, and it represents the object circumscribed by the line, the tendency of the object to rotate. Okay, let me check back with any questions here. Okay, I don't see anything right now. Please put down the questions if you see them. Okay, we talked about how line integrals can be taken on an open or closed line. When line integrals are taken on a closed line, there's a special thing that you can apply called the Stokes theorem. So I'll just put that here, that the Stokes theorem applies on closed lines. So just keep that in mind. You can do line integrals. This is a closed line. You can do line integrals on closed lines. You can also do line integrals on open lines. Okay, but when you have a closed line like this, then the Stokes theorem can be used to as an alternative way to calculate the circulation. All right, and we'll get into that in just a second here. All right, the first thing we're going to do is how to calculate a line integral. We went over this at the end of class last time. I would like to go over it again using a very methodical approach to doing it. The point of the end of last class was to show you just the intuition of what a line integral is. So let's go over that again real quick, and then we'll go through our strategy for finding line integrals, which applies in all cases. So you have this vector field A. So you can see that this is A here. A is equal to 0, 0, comma 3y. So 0 in the x-hat direction, 3y in the y-hat direction. You can see that the vector field has no x component, right? They're all vertical arrows, right? Because this x component is 0 and the y component is 3y. You can see that the y component is getting larger the farther you go up the y-axis. So this is the y-axis here. That wasn't obvious. Here's the x-axis here. Okay, now the intuition that I wanted to mention to you last time is that this A dot dl, right? You figure out what is A, what is dl, and what is A dot dl. Okay, now here on this, the first line that I'm asking you to look at the line integral for is a horizontal line extending from x going from 2 to 5 and at y equals 2. So we're talking about this line right here at y equals 2. Okay, so let's just let's put that on here. So in this case, you can see that the line is horizontal. Okay, and so when you do this strategy, a shortcut that you can use in this problem, it only applies to this specific problem. So you can see the intuition is that, okay, you figure out what A is. We know what the A vector field is that's given to us. What is dl? Okay, in this case, in this simple case, dl is actually, it's just, dl is always tangent or parallel to the line that you're integrating on. And in the simplest case of just a horizontal line like this, the unit vector that points, that's always tangential to the line, is just x hat, right? Because this line is horizontal, so the tangent vector is always pointing in the x direction. So in this first example, A is equal to 0x plus 3y, and then dl is equal to dx times x hat. Okay, you have to have the dx in there as well. And then so the third step is you figure out A dot dl, and that gives you 0. So this line integral ends up being 0. Now, intuitively, why is that the case? Well, think about this. This is the integral, line integral is A dot dl. Okay. What do we know about the dot product of two orthogonal vectors? So I'm going to put this question out. Let's see if someone can answer that. What is the dot product of two orthogonal vectors? 0. That's right. Thank you, Bilal. So when we're doing the line integral along this horizontal line, a dot dl is basically equal to 0, because you can see that a is always perpendicular. A is only pointing in the upwards direction, and then dl is pointing in the horizontal direction. So there's always a 90-degree angle between the vector field and the line. So in this case, a dot dl is going to be 0. But you can do it mathematically, and that can work too. Along the second line, we did this example of where we actually had to figure out what the a dot dl is. So we know what a is. dl in this case, in the vertical line, is just a y hat times dy, because now you have a vertical line. So your differential vector is going to be going in the y direction. So dl is equal to dy times y hat. And then you take the dot product of a dot dl, and notice that in this case, it's not equal to 0. All right. So when we take the line integral, we take the line integral from y is going from 1 to 6, and x equals 3. We have our limits of integration here. Y is going from 1 to 6, and x is equal to 3. And we plug that into this equation here, and we create our integral. So you have 3y dy, and where y is going from 1 to 6, and we figured that out last time to be 52.5. All right. So now what I'd like to do is I'd like to show you a more mathematical way of approaching this problem. Okay, and we'll use that mathematical approach in the second example. All right, suppose we have a field A is equal to y times y hat. Find the line integral a dot dl along the line y equals x squared from x equals 0 to x equals 1. So notice in this case, the line that we're integrating across is not just a horizontal line, it's not just a vertical line. So the dl vector, let's do this here. So notice that, if we're at this particular point in space, the dl vector is going to be pointing in this direction. Out here, dl is going to be pointing in a different direction. So we can't use the simple definitions that we used in that last example. So I'm going to show you a strategy that you can use that applies to all problems. All problems. Okay? The strategy is in this box, but I'll show you an example of how to do it. Okay. So the first question is, what is A? So A is equal to y times y hat. Okay, sorry. The second part is, what is dl? Now this is the mathematically rigorous way of finding dl. All right. So what is dl? So the first thing you have to look at is what coordinate system you're using. All right, in this case, we are in the Cartesian coordinate system. And based on that Cartesian coordinate system, you can actually just look up what dl is on the charts. So let's go back to our handy chart here. Just give me a second here. Right, in the Cartesian coordinate system, the differential length vector dl is going to be equal to x hat dx plus y hat dy plus z hat dz. So just remember this, and it's different in the cylindrical and spherical coordinate systems. So x hat dx, y hat dy plus z hat dz. So let's go back to our example here and use that. All right. So our definition, dl equals x hat dx plus y hat dy plus z hat dz. All right, in this case, we are not in a three-dimensional coordinate system, so our dz is going to be 0. So this we can get rid of that right away. So our dl is x hat dx plus y hat dy. Now what we have to do is we have to look specifically along this line y equals x squared. All right, so we have to take this information into account. So let's write this down. Y is equal to x squared. That's our line. Now, in order to figure out dx and dy, what the relationships between those two are, we have to take the derivative of this and find the relationships between dx and dy. So let's take the derivative of this. So we can say dy dx is equal to 2x. All right, and from here we can go and say that dy is equal to 2x dx. And I'll show you why that's important in just a second. All right, so all we've done is we've looked at our function that defines the line, and we've taken the derivative of it, so now we have a relationship between dy and dx. Okay, so now going back to the previous thing, we figured out what dl is. Now, here's the trick. What we want to do is we want to define dl in terms of a single variable. When you do a line integral, the whole point of a line integral is that you're going to integrate one variable. So a line integral means integrating one variable. All right, we can see that our dl here, our dl is a function of x and y. So we're going to transform that into a single variable that we can then that we can use to do the integral. Okay, so what I'm going to do here is we're going to integrate with respect to x. X is going from 0 to 1, right? So we want to put everything in terms of x. So we want to define dl in terms of x, because we're going to be integrating in terms of x. All right, so our dl is equal to x hat dx all right, x hat dx. Now we substitute here. We have y hat dy. All right, we want to get rid of that dy because we're going to be integrating with respect to x. So we substitute this in. dy is equal to 2x dx. So this will be y hat times 2x dx. All right, and so now we have a new relationship for dl. This is dl in terms of x. That's the key thing. This is the key step for doing the line integral. All right, so notice that we took into account what our line is. Well, we have y equals x squared. We found a relationship between dy and dx. And then we put dy in terms of x and dx, and we substituted that in here. So now our dl function it has x hat and y hat components, but the magnitudes of those it's all in terms of x, and that's where we're going to be integrating. All right, so the next step is a dot dl, right? And the next step, really, I'm just going by this chart here. What is a? What is dl? What is a dot dl? So a dot dl equals y times y hat dotted with dx times x hat plus 2x dx times y hat. All right, and the dot product of those, you multiply the x components together, and we see that a doesn't have any x component, so that will be 0. So it'll be 0 plus. We multiply the y hat components together, so 2x dx times y. Okay, all right. So notice here we still have this y variable here. All right, if we're going to integrate with respect to x, we can't have this y here. We have to put everything in terms of x, because we're only integrating with respect to a single variable. But again, we look back to here. We say, well, y is equal to x squared. All right, so we substitute that in to get rid of the y. All right, so we end up with 2x, we have our dx here, and for y we substitute x squared. And so we're left with 3x cubed dx. Okay, so this is the part where we basically converted, we figured out a dot dl, and we've converted our function, we've converted our a dot dl, a line integral, into just a scalar integral. So the next step is, what are the limits of integration? So we're going to be integrating from x equals 0 to 1. Right? And the last step is just to do the integration. So integral of a dot dl is equal to the integral from x equals 0 to 1 of 3x cubed dx oh, this should be 2x cubed, I'm sorry. I made a mistake here. So let me just erase that quick. All right, so this is 2x cubed. We have 2x cubed here. And this comes out to 1/2 times x to the 4th, going from 0 to 1, and that comes to 1/2. So the integral of a dot dl is equal to 1/2 here. Okay. All right, let's go back and look at any questions. Shouldn't it be 2x cubed? Yes, thanks, Bilal. You caught that. Good. All right. So any questions? All right. The key part of the strategy is that you have to transform everything into a single variable. So dl is equal to x hat times dx plus y hat times dy, but then you put everything in terms of x, right? And where does that extra information come from? It comes from the line that you're integrating across. All right, so let's do another example here. This one is in cylindrical coordinates. So we have a vector field f of x, y is equal to 0x, and that is in, excuse me, that is in cylindrical coordinates. I'm sorry, this is given to you in Cartesian coordinates. So this is in Cartesian. And you're asked to find, using a line integral, compute the work done by the force field on a particle that moves along the curve C that is counterclockwise, the counterclockwise quarter unit circle in the first quadrant. So in the picture below, the curve C is plotted by the long green arrow. The vector field F is represented by the vertical black arrows. Okay, so this solution is it's involved. So I want to go through all the steps with you. And in fact, I may do the solution on a separate, in a OneNote so that you can see it easier. Okay, so I'm just going to hop back and forth between these two. Okay, so the tricky part about this problem is that you are given a force field, and the force field is defined in Cartesian coordinates. However, you are integrating across, along a quarter circle, right? So the question is, and I want to ask everyone this, so everyone please give their inputs here. Which coordinate system should we use here? Okay, spherical coordinate system, that's one suggestion. What other suggestions do we have from the class? It's okay if you're not sure. Spherical coordinate system. Okay, so John also selects spherical system. Okay. Let's break this down. Let's look at why. So why do you guys think you'd want to use a spherical system? Bilal is typing something. So. Amar suggests cylindrical. Bilal suggests cylindrical. So let's start with the spherical first. So Arad, you had first said spherical, and then you changed to cylindrical. What made you change your mind? Exactly. You got it. It's a constant, like this line that we're integrating around is a constant r with changing theta. Absolutely. And John is typing something. Let's wait for him. Okay, so John, you also see that why the cylindrical system might be better in this situation. So we're looking at these when we're looking at these coordinate systems, we have to think about we're integrating across a line here. And it's true, if you wanted to do this problem in spherical coordinates, you certainly could. The question is, which one is going to be easiest? Since we are integrating across the elements of a circle here, the cylindrical coordinate system is probably the easiest one to use. The spherical coordinate system will also work. That would probably be the next easiest one to use. And the Cartesian coordinate system would actually be not the best one to use in this case, because when we're integrating along like a circle here, the Cartesian coordinate system doesn't do it doesn't naturally represent circular symmetry. Okay, so we're going to choose to do this problem in cylindrical coordinates. However, we have this problem here. Oh, that's great. I got my FedEx delivery. Thanks. Now all of you know. The problem here is that the force field that's given to us is in Cartesian coordinates, and we want to do this problem in cylindrical coordinates. So what I'd like to show you is that you can actually convert a force field, you can convert a vector field from one coordinate system to another. So I want to first show you how to do that. Let's keep our ink annotations, and we'll go back to our chart. I want to show you how you can use that chart to do transformations. Again, you'll have this chart on the exam, so no worries. You don't have to write all this stuff down. So this one was the vector properties. This one is about coordinate transformations. So let's look at this slide. So what we'd like to do is we have a vector field that's defined in Cartesian coordinates, and we want to convert that into cylindrical coordinates. So what we have to do is we have to use these sections here. R is equal to the square root of x squared plus y squared, phi is equal to tan negative 1 of y over x, and z is equal to z. So this is how you transform coordinates, and this is how you transform unit vectors, and this last one is how you transform the vector components. So we're going to be using this one primarily, and also the coordinates as well. So AR is equal to AX cosine of phi plus AY sine of phi. A phi is equal to negative AX sine phi plus AY cosine phi, and so forth. So what this is doing is, like, if you have vector components in x, y, and z, so the components in x and y and x, y, and z, suppose you have a Cartesian vector. You have x, y, and z components. So this is your AX, AY, and AZ. So you're going to be calculating, by doing this transformation, you're going to be calculating the AR, A phi, and AZ. So you're going to convert that vector into a cylindrical coordinate system. All right, let's see if there's any questions. Okay, good. All right, let's go back down then to our problem. All right, like I said, this one's kind of involved, so I'm going to open up the PowerPoint here. Or OneNote. All right. So we are going to be integrating along this quarter circle, all right, and that r is equal to 1. All right, here's our x and y here. And I'm not going to bother drawing the vector field because it'll just, it's going to make the graph cluttered, all right? So we are going to be integrating along this portion of the line. All right, and our f of xy. So the vector field is 0 times x hat plus 3y times y hat. Oh wait, no, I got that wrong. Here. The vector field is just x. It just has a y component, so x times y hat. Okay, so how do we solve this problem? The first thing we have to do is we have to choose a coordinate system. So using our same strategy, we have to do what is A, what is dl, what is A dot dl, what is the range of integration, perform the integral. So in this case, we actually have to do some work on this first step, what is A? Because we're going to do this problem in cylindrical coordinates, but our A is given in Cartesian coordinates. So the first step, what is A? So let's do a conversion. Okay, so we're going to use the formulas that we have there. So we have the AX, AY, and AZ components. So our AX component is equal to 0. Our AY component is equal to x, and our AZ component is equal to 0. So 3 components of our vector field, and we're going to convert that into cylindrical. So the way we do that is we're going to use the formulas that I showed you earlier. So AR is equal to AX cosine of phi plus AY sine of phi. All right, and since this AX term, AX is equal to 0, so this goes away, and you're just left with AY sine of phi. All right. Oh, I'm sorry. No. The AY is equal to x. You can see this here. So this is equal to x sine of phi. All right, now the next component, a phi, the formula for that is negative ax sine of phi plus ay cosine of phi. All right, again, this x, since our ax term is 0, you're just left with the second term, ay cosine of phi. So this becomes x cosine of phi. Okay, all right. Now, we also have to convert some of these guys over because we're eventually going to be doing this problem in cylindrical coordinates. So we need to do a coordinate transform as well. Let's remind ourselves, from the table, we know that x, we have to transform the coordinates. So this is given in x. We want everything in terms of r, phi, and z. So x is equal to r times cosine of phi, and y is equal to r times sine of phi. All right, so this x sine of phi becomes r cosine of phi, and then that is multiplied by sine of phi. All right, so the a phi term becomes let's see, r sine phi cosine phi. Okay, yeah, get that right? Okay. Let me double check. Okay, good. So now we figured out our vector field. Our vector field f of r, phi, and z. The z component is 0, okay? Oh, I'll just put that here just to be explicit. AZ is equal to AZ, and that is equal to 0. Okay, so our vector field is r sine phi cosine of phi times r hat plus r sine phi cosine of phi times phi hat. Okay, so we converted into cylindrical coordinates. Everyone with me so far? Let's see if there's any questions. Arad? Isn't it supposed to be cosine squared for a phi? Yes, yes, thank you. Thank you for catching that. All right. I was wondering why it looked a little bit different here. Thank you for that. Okay, so this is x is equal to r cosine of phi. So this is going to be r cosine squared of phi. Thank you. All right, so we've converted our field over into cylindrical coordinates. All right, any other questions? Thank you, Arad, for that correction. Okay, good. So now the next step, what is dl? Okay, so the thing here is we are in a cylindrical coordinate system. And again, just to belabor the point, I'm just going to go back here again to the chart and show you how you can use the chart here. The cylindrical coordinate system says that this is the differential length vector is going to be r hat dr plus phi hat r d phi plus z hat times dz. So we take that in our coordinate system. dr times r hat plus r d phi times phi hat plus dz times z hat. Okay, in this problem, since it's two dimensions, obviously that dz term is going to go away when we do the dot product. Okay, so the next step is what is a dot dl. Okay, so we multiply the two together, or in this case it's f dot dl, not a dot dl. F dot dl is we're going to take the cross product of f and dl. So the r components are going to multiply together, the phi hat components are going to multiply together, and the z hat component is basically going to be 0 because there's no z hat component of f. So let's just multiply these two together here. So we get r sine theta, or r sine phi cosine of phi times dr. R sine phi cosine of phi dr. And then we're going to add the phi term. So we're going to get r squared cosine squared of phi d phi. R squared cosine squared of phi d phi. All right, so we have a scalar function here. Remember, this is not a vector function. After you take the dot product, it becomes a scalar. So then it really just becomes a question of integrating this function. All right, so what is our next step in our strategy? Is that we have to find the limits of integration. What is the line that we are integrating across? Okay, in this case, we are integrating across this a line that's represented by a quarter circle. Can someone in the class tell me what are going to be the limits of integration for r and phi? I'm sorry, we're only integrating a single variable, so there's going to be a range of a single variable. Okay, so I want to rephrase the question and say, like, what is r and what is phi during this integration? Bilal is typing, so wait. Okay, great. So thank you, Bilal. So phi is going from 0 to pi over 4. This is correct, right? Phi is going from 0 to pi over 4. Why is that? Well, you're going from this portion of the circle into this portion of the circle. The second part, I just want to make a correction here, is the r is not going from 0 to 1. Actually, the r is just equal to 1, right? Along this line, everywhere along this green line, r is equal to 1. So this is the difference between a surface integral and a line integral, is that in a surface integral, you integrate over two different variables. So both of your variables are going to have a range. like this. But in the case of a line integral, only one of your variables is going to have a range, and the other variable is going to be fixed. So that's an important distinction here. So this next step here, finding our range of integration, in our line integral problems, there's only going to be a single variable that's where we're going to have a range. So phi is going from 0 to pi over 4, as Bilal said, thank you. But r is going to be equal to 1, right? So our integration is really just over the single variable, and we are just going to be substituting r equals 1 for everywhere in our equation. So the last part is to do the integral. So we are going to be taking the integral of f dot dl along this line. And this is going to be the integral. We're going to be taking phi going from 0 to pi over 4. Our f dot dl is r sine phi cosine phi dr plus r squared cosine squared of phi d phi. Okay, now this is where our ranges of integration play an important role. Okay, so our r is equal to 1 everywhere. Okay, so we can also figure out what dr is. So what is dr? We take the derivative of both sides. Dr is equal to 0. All right, when we take this r equals 1 and dr is equal to 0, and we substitute that in here, so our dr is equal to 0 here, r is equal to 1 here, r is equal to 1 here. Okay, when we do that, then our equations simplify more. All right, since our dr is 0, this term just goes away completely, and we're left with just the second term. And we substitute r equals 1 here, then we're just left with phi equals 0 to pi over 4 of 1 squared times cosine squared of phi d phi. So we're just left with cosine squared of phi d phi here. Okay, you see this? So whenever you do line integrals, you have to look carefully at what line you're integrating across, and that will actually simplify your equations. So if we look back at this previous example, all right, we were integrating along the line y is equal to x squared. So we said y is equal to x squared, dy dx, we have found a relationship between dy and dx. And when we had our range of integration, we said our x is going from 0 to 1, right? Our range is going, x is going from 0 to 1, but we also said the y, sorry if this is a different color. Y is equal to x squared, and dy equals 2x dx. I'm being redundant here, but I want to show you like the analogy of what we're doing in this problem, in the second problem. We have a range of x that we're integrating, but then we also have a relation of how y is related to x in this case. We're also looking at that second variable, but we're only integrating with respect to 1. The second variable is being used to substitute in values so that everything is in terms of a single variable. The same thing we did here. All right, you can see that our f.dl is in terms of two variables, r and phi. But when we're integrating from phi is equal to 0 to pi over 4, so obviously this has to be a variable that we're integrating based on. The other variable is fixed. R is fixed, so we can just substitute in values for r and dr, and that gets rid of our r variable so that in the end we are only left with an integral that's a function of a single variable. All right, so that's the most important part about doing these line integrals, is taking f.dl, which will often be a function of two variables, and then transforming it into an integral of just a single variable. All right, so when we do this, let's see. Yeah, in order to solve this integral, I think, hold on, pi over, I think we have to fix something as well. Our range of integration is should actually be from 0 to pi over 2. So we're going 90 degrees, so it's pi over 2. So let me fix that here. Pi over 2. Okay. Now the integral of cosine squared of d phi, this is something that you can look up on an integral table, and that's how I would suggest that you do that. So the integral of this is 1/2 times phi plus sine of 2 phi over 2, and our limits are 0 to pi over 2. Okay, and then this comes out to 1/2 times pi over 2. This term, the sine of 2 pi times pi over 2 has become sine of pi, which is 0. And then you subtract out 1/2, and you substitute in 0 here. You get 0 for both of these terms, and so you're left with pi over 4 as your line integral. Okay, so this is your final answer here. Okay, so we took the line integral of this vector field dotted with dl over this quarter circle like this. All right. So, questions? Okay, Mohammed, you brought up the same point. Thank you for that. It is pi over 2. It is pi over 2. So thanks. You know, this is really great. That means I can see that all of you are following along in the notes, and you're fixing the mistakes I made, so that's great. That means we're all on the same page here. Okay, let's have any questions. Are there any questions on how to do the process of doing line integrals? Okay, great. Let us continue then. All right, the next part is Stokes theorem. So just like we had a theorem when we were doing surface integrals, for surface integrals there was the divergence theorem. And for line integrals there's something called the Stokes theorem. And the Stokes theorem, if you haven't guessed already, it tells you two different ways to calculate the circulation of a surface bounded by a contour. All right, in the case of the divergence theorem, we found two different ways to calculate the net outward flux from a closed surface. In the Stokes theorem, there's two possible ways to calculate the total circulation of a surface S that's bounded by a closed contour. All right. So the first way of calculating the circulation is the example that we just did in the previous example there. All right, we took the line integral. We took a dot dl, and we took the integral of that along a closed path. Actually, the example that we did was actually an open path. We didn't go all the way around the quarter circle. We only went through. So that was an example of an open line integral. But if the line integral is closed, so if you have a line that is completely encloses a contour that completely is closed, so that it will describe a surface inside of it, it will circumscribe a surface inside of it, then you can use Stokes' theorem to figure out the circulation of that surface. Okay, there's two ways you can find it. One way is by the line integral. The second way is using the Stokes theorem, which says that the circulation is also equal to the curl of the vector field A dotted with ds, and ds is the vector that is normal, the differential vector, the differential surface area vector. So it's n hat, and n hat is perpendicular to the surface, and then the magnitude is equal to ds, which is, it depends on what coordinate system you're in, but you can figure out what this ds is. We'll look at an example of that. All right, so why would you want to use the Stokes theorem? This is useful for converting a line integral around a contour into a surface integral of the area contained by the contour. So when you do these types of circulation problems, Stokes theorem helps you out in a few ways. One is that you could actually calculate it both ways. And Stokes theorem tells you that both are equal to each other, so you can use that to check your work. The other thing it does is that certain situations it may be easier to actually calculate del cross A, to calculate the curl and do it this way. And in other situations it may be easier to actually calculate the line integral around the outside and then figure out the circulation that way. But there's two ways to skin the cat, just like the divergence theorem. So what does this physically mean? All right, the circulation of a surface S, this is the tendency of this surface. If we were to place this surface in a vector field, the circulation would represent the tendency of this contour to rotate. So for example, if I happen, this graph shows A here. Let's say, for example, A is, the vector field A is pointing down in this direction, and then the vector field A is pointing up in this direction. Okay? So what direction is this surface, this object, what direction is it going to rotate? I'll look at the answers here. Which direction would that surface rotate? So I'll go back to the graph here. So I've drawn an imaginary vector field A, which has the arrows shown here. So the arrows are pointed down in this direction and they're pointed up in this direction. So what direction would this surface rotate? Counterclockwise. Exactly. You imagine like a force going up on this side and a force going down on this side. That would cause this contour to rotate. And because, if there is a tendency for that contour to rotate, then there is circulation. That means that there would be a circulation for this surface S. So these are two ways to actually calculate that circulation. And just as another example, positive circulation means that you're rotating in the counterclockwise direction. A negative circulation means you're rotating in the clockwise direction. So if our vector field looks something like this, where we had vectors pointed upwards on this side and vectors pointed downwards on this side, in this case, this is the opposite situation where the object would actually rotate clockwise instead of counterclockwise. It would rotate clockwise, so this would have a negative circulation. All right? So that's the physical meaning of what the circulation is and how Stokes' theorem can then be used to calculate it. So here's the intuition of circulation in the Stokes theorem. This is a nice graph that was from this book, Elements of Electromagnetics by Sadiku. Imagine that this is your surface S. So this is the surface. Or this whole thing is the surface, rather. This whole thing is the surface. We just erase the ink on the slide. So this whole thing here represents the surface. Now, there's two ways of figuring out the circulation there, the tendency of the surface to rotate in a vector field. One is by looking at, by doing the line integrals all along the edges like this. Okay, and what you're doing there is you are adding up the forces, the tangential forces that would cause this thing to rotate. So you're adding up the forces that are parallel to this line, adding up the forces perpendicular to this line, adding up the forces perpendicular to this line, and so forth for this line. by taking the force components that are only along this counterclockwise direction, you are getting the tendency of the entire object to rotate in the counterclockwise direction. So that is what the circulation is. So that would be the right-hand side of the equation here. The left-hand side of the equation, what we're doing is we are going to break up that surface into a bunch of tinier surfaces. So each one of these little surfaces is a differential surface, and we're taking the curl of that particular differential surface. So the curl represents curl of A, in other words, del cross A, is the tendency of a certain point to circulate. Tendency of a point to rotate counterclockwise. So essentially what we're saying is that the tendency of this entire surface to rotate is the sum of the tendencies of each one of these little areas inside of it to rotate. So this has a tendency to rotate, this may have a tendency to rotate, this one does, and by adding all of those guys up and by integrating the curl over this entire area, that will also give us the circulation of the surface. Okay? Questions? All right. Great. So let's do an example. Verify the Stokes theorem for the vector field B is equal to Z cosine of phi divided by R. So this is an example that was in the in our textbook. Okay, and this is just giving you Stokes theorem. All right, so this is the left-hand side of the equation, and then this is the right-hand side of the equation. So what we want to do is when we're verifying the Stokes theorem is we want to calculate, our strategy is to calculate this side of the equation and then calculate this side of the equation. So this will be, let's see, which one are we doing for? Yeah, this will be step 1. And then we calculate the right-hand side of the equation, that's step 2. And by the Stokes theorem, they should match each other. All right, verifying the Stokes theorem for the vector field B is equal to Z hat times cosine of phi divided by R. So we're given a vector field, and we can kind of just imagine that this vector field is in the Z hat direction. It's only pointed upwards. And then we're looking at the circulation of this surface enclosed by this contour. Okay. All right, so how do we go about doing this problem? We can do the left-hand side of the equation, right-hand side of the equation separately. And I've actually just, rather than write all of this one out step by step, I'm going to show you the solutions from the book. The first you calculate the curl, and then you perform the surface integral. So that's your strategy here. And I really would like for you to all go over this on your own in the book. I'll talk about it step by step right now, but I really think the best thing to do is for you all to go through this example on your own and make sure that you're able to do it. All right. So step 1, I'm just going to annotate some of these things for you so that you can see it, the major steps and process of how to do it. So step 1 is calculating the curl. So the first part here is calculating the curl, and then the second part is doing the surface integral. Second part here. Okay. Now, so what we're doing is we want to find the del cross B dot ds. Okay, so the first thing we want to find del cross B first. So how do we calculate the curl? Well, you guys have done examples of how to calculate the curl in your homeworks. I hope that you've if you haven't completed that yet, that's going to be due tomorrow. But in that homework, you actually have examples of where you're calculating the curl, the divergence, and the gradient in different coordinate systems. All right. So in order to find the curl of this field, we are in a cylindrical coordinate system. So we have to again go back to that chart, the charts we had earlier. Give me a second here. This chart gives you the vector operations in other coordinate systems. So we want to calculate the curl of a vector field in the cylindrical coordinate system, and so we use this set of formulas here. And really the best way for you to get familiar with it is to actually do example problems of rather than just looking at the formulas. You really need to just practice a little bit on those. So that's what we're doing here. So we look up the formula for del cross B, the curl of B in the cylindrical coordinate system, and we have an r hat component, a phi hat component, and a z hat component. All right, after we do some of the calculations there, we find that there's an r hat and phi hat component left. There's no z hat component. Okay? So the r hat component is 1 over r d bz d phi, and then d b phi dz. So if we want to, I suggest you actually go over some of these things separately, but just to give you a general idea, this is giving you bz. So this is just giving you the bz component. So I'll just put this here. Bz equals cosine of phi divided by r. So when you're figuring out the components of the curl, you're going to be asked to do a lot of partial derivatives. So you're going to be taking dbz over d phi. So I'm just giving you an example here, dbz over d phi. We take the partial derivative of this with respect to phi, and so we treat r as a constant. And so this becomes negative 1 over r sine of phi. Okay? And then the next part here is db phi dz. And of course this comes out to 0, right? Because phi, b phi dz, phi is equal to 0, so of course this term is then becomes equal to 0. So this is how you go about doing these types of problems. You have to figure out a lot of different partial derivatives, and then you will go through and get a formula here that gives you del cross B. All right, standard figuring out the curl. Notice that the curl has components in the r hat direction and in the phi hat direction, and this depends on 1 over r squared. Okay? All right, so after you figure out the curl, since this is a vector quantity, now you have to figure out del cross B times ds. So you're doing a surface integral here. This is your vector field, and then this is your surface integral. So I'm going to go here and so we want to find the integral del cross B times ds. So our step 1 is del cross B, and that del cross B is given here, sine phi over r squared. plus cosine of phi is phi hat cosine of phi over r squared All right, the second step is what is ds? All right, and what ds comes out to is dz times r d phi. And the reason for that, we are integrating along a portion of the cylinder. Okay, so if we take a small differential element of it, this is going to be dz, and the differential element here is going to be r times d phi. All right, and so the ds is going to be equal to dz times r d phi, and it's going to point, the normal is in the r hat direction, so this is going to be r hat here. Okay, and then the third part is you have to find the limits of integration. So when you're going to be integrated from z equals z equals 0 to 3, phi equals pi to 3 of pi over 2. This is a surface integral, so we are integrating across two variables. Okay, so we actually skipped a step here. We didn't do del cross b dotted with ds, so you could just take the dot product of these two vectors, and that's what is shown here. Okay, this is your del cross b. Your ds vector is given right here. You take the dot product of the two, and you get this function here, and you integrate that from phi going from pi over 3 to pi over 2, and z going from 0 to 3. Okay, notice that just like before, after you take the dot product, this becomes a scalar function. In this case, it's just sine of pi over r, times d phi dz. And notice that we are at a fixed r, so the r goes away. The r will, you can substitute in a value for r because you are at a fixed value for r in this case. Okay. Okay, now the next part, the right-hand side of the equation is you have to figure out b dot dl. Now this part, you have to do a 5-step line integral strategy for every single segment. So we did, in our example, we did line integral. I showed you the 5-step process for doing a line integral. Now, if you want to figure out the circulation using the right-hand side of the equation, you have to add up the line integral contributions from every edge of this contour. So what do I mean by that? Okay, so this is the contour that we're talking about here, right? So we have to, if we want to find the line integral around this contour, so where my mouse is showing here, we're going in the counterclockwise direction. Go from C to D, from D to A to B, and then B to C. So in order to find this right-hand side of the equation, b dot dl around a closed contour, we actually have to add up the contributions from every edge on the edge around that contour. So we have to figure out the line integral from C to D. Then we have to find the line integral from D to A, then from A to B, and then finally from B to C. And so that means we have 4 different line integrals that we have to do. So obviously you can see that in this particular problem, maybe this one may actually be easier to do using the left-hand side of the equation. The right-hand side of the equation turns out to be not too bad either, because it turns out that 3 of the terms actually drop out. So the term going from A to B the one going from B to C, from C to D, and so forth, all these three terms drop out, and you're just left with this one. Why do these terms drop out? I suggest that you go through the math yourself and prove that to yourself. But I'll give you a little bit of a hint here. Is if we look at what this function is, you notice that B is only in the z hat direction, and it's cosine of phi divided by r. Okay, so the vector field is pointing in the up and down direction. Okay, it's just in the vertical direction. Now, if you have these components, if you're going from C to D or from A to B, then you'll notice that the line that you're integrating along, so let me just draw this, the vector B is always pointing in a vertical direction, but you are integrating along this line here, so your DL is going to be pointed in this direction. In the lower integral, your DL is going to be pointed in this direction. So you notice that your DL and your B, they are perpendicular to each other. B is pointed vertical, and then DL is pointed in the phi hat direction or negative phi hat direction. So these are mutually perpendicular to each other. So that's why these two, the C to D segment and the A to B segment, they basically go to 0. And if you recognize some of these symmetries beforehand, you'll save yourself a lot of time on these types of problems, because you can see that this could get pretty involved mathematically. So you can see that these two terms basically go to 0. And if you go and do the math, you'll find that this term also happens to go to 0 when you do that. So you're left with just this integral A to D, and we go through that 5-step process of the line integral. I can just to make sure that we're all on the same page, we can go through some of those steps with you. So this was the left-hand side, and then this is the right-hand side. So integral from A to D of b dA dot dl, b dot dl. Okay, let me check if there's any questions first. Any questions here? No? Okay. All right, the first step is what is B? We already have a formula for B. So it's equal to z hat cosine of phi over r. And the next stage is dl. In the cylindrical coordinate system, dl is equal to r hat times dr plus phi hat times r d phi plus z hat dz. All right. The third step, what is b dot dl? So we take the dot product of these two together, and of course the r hat and phi hat components don't exist in B, so you're only left with the z component. So you're left with cosine of phi times 1 over r, oops. Let's make this a little bit bigger. Cosine of phi times 1 over r times dz. Okay, step 4, the limits of integration. So this is where we need to look geometrically at which part of the line that we're on right now. So we're looking at line going from D to A. So we are at on this left side of the contour here. So we are going along this line here from D to A. Okay, so we have to think about what variables are we integrating along that line. So along this line, the variable of integration, the z, is changing. So we're going from z equals 3 to z equals 0. All right, and we are at a fixed radius, and we are at a fixed value of phi. So phi here is equal to pi over 3, and our radius is equal to 2. So we're going to put down our integration variables. So our z is going from 3 to 0. Okay, now there's actually a very important point that I want to make here. So we are going in the counterclockwise direction. Okay, so we actually want to be going from D to A. All right, so our limits of integration have to go from D to A. So let me correct that here. Okay, I want to make sure that everyone gets that point. This is one of the most important points about doing line integrals, is when you're doing multiple segments of a line like this, you do have to make sure you're going in the right direction. So when we do a line integral, we have to go in the counterclockwise direction. So when we're on this side of the contour, we have to go from, if we're going in the counterclockwise direction, we have to go from D to A. All right, so our limits of integration are going to be from 3 to 0. The phi is fixed at pi over 3. And the r is fixed at r equals 2. All right, and the last step is to do the integral. So integral from d to a b dot dl. It's going to be equal to, you're going to go from z equals 3 to z equals 0. B dot L is 1 over r cosine of phi dz. And we substitute our variables in here so that we're only left with a function of a single variable. Z equals 3 to 0. Phi is equal to pi over 3. And r is equal to 2. So we're left with 1/2 cosine of pi over 3 dz. Cosine of pi over 3 over 2. That variable comes out, and the z goes from 0 to 3. So this is going to be z going from, that's why you get this negative sign here. Times negative 3. All right. So when you do that, you end up getting negative 3 over 4. Okay, well, you got that right there. This term, after you do the math, this should come out to negative 3 over 4. I didn't go through all the arithmetic steps here. All right. So notice that we did the math on the left-hand side. The way we did that is to first calculate the curl, and then we found the surface integral of the curl function. On the right-hand side of the equation, we had to use a 5-step line integral, five-step strategy for the line integrals, and we had to do 4 different line integrals. Fortunately, 3 of them turned out to be 0. And then the second step is that we add them up, right? And then we notice 3 of the terms drop out. We add them up and we find that the line integral is equal to 4. Now, regardless of which approach you used, the line integral approach or the the curl approach, the answer is the same. The circulation comes out to -3/4 in both cases. All right, so it's a good way to check over your math. Make sure you did it right. Okay. Any questions on that? Okay. So like I said, great way to study is to go over and do this example problem on your own. Make sure that you can do it on your own without anyone's help. There's a homework problem. Another one that I'd like to give you is, if you're looking for extra practice on how to use the Stokes theorem, here's an example. Calculate this. You have this vector field and calculate the total circulation over a quarter circular disk with radius 3 in the first quadrant, and do this calculation using both the left and right hand sides of the Stokes theorem. So a quarter circular disk will look something like this, as we saw before. So this is r equals 3, but you're also going to be finding this portion here and as well as this one. So you're going to be going counterclockwise in this quarter circle, okay? And you're going to find the line integrals. There's 3 line integrals that you have to do, 1, 2, and 3. And then you also find this the circulation using the Stokes theorem as well. So the challenge I'm going to give you on this problem is figuring out what coordinate system to use. And if you really want to know this stuff, you can actually try it in both and see which one's easier. But you will definitely find in this problem that it's easier to use one particular coordinate system than the other. Okay, and I'll let you figure out what that is. It may or may not be the same as what we did in the other problem where we were just integrating along this line. Okay, so you figure it out which coordinate system you want to use. If you decide to use cylindrical, you have to remember to convert this over into cylindrical coordinates and do everything in cylindrical. And if you choose to use the Cartesian system, you have to make sure that you define all of these lines. You have 3 different lines that you're doing integrals across. You have to define all those lines in Cartesian coordinates, not cylindrical coordinates. Okay, so see which one works better for you. All right, the last few minutes to wrap up this chapter is just doing the classification of vector fields. There are many different types of vector fields, so it is useful to classify them and have just jargon to be able to classify the vector fields so that you immediately know what kind of field that you're dealing with. So here are the definitions. So if you have a vector field A, if the divergence is 0 everywhere, then A is solenoidal. Okay, divergence means you have divergence. Remember, it means that you have vectors going out of a certain point or into a certain point. Okay, and if the divergence is 0 everywhere, then you can say that the definition is that the A is solenoidal. Solenoidal means it has no sources and no sinks. A source would be something where the field vector lines are going away from there, and it has a positive divergence. A sink is where you have the vector lines going in, and the divergence is negative at that point. Okay, so if the divergence is 0, that means you don't have these sources and sinks, and the flow is solenoidal. If the curl is 0 everywhere, then A is irrotational. Remember, curl is a measure of how much of a field rotates. And if there's no curl, then the field is irrotational. If the divergence and curl are both 0, then A is considered a Laplacian field. And some of these other things, this last one here you may not use in this class. If the divergence and curl are specified everywhere, then A is determined. This is the Helmholtz theorem. So specified means that the divergence and curl have solutions everywhere. So, if you find that the curl happens to be 1 over r, and then at r equals 0, the curl is going to be not defined. So that's an example of where the curl is not defined at a specific point, right? So if it's specified everywhere, then A is determined. If A is a gradient of a scalar function, then A is considered conservative. So one example of that is when we talk about scalar potential, we're going to be talking about scalar potential V, which is given in volts. It turns out that E is the gradient of V. So E is the gradient of a scalar function V. Therefore, electric fields are conservative fields. Conservative fields are always irrotational, not necessarily the other way around. The line integrals of conservative fields from point P to Q is always the same regardless of path. I'm not going to focus on this right now. This will become a lot more clear when we start talking about scalar potential. But I just want to mention to you that electric fields are considered conservative fields because they are the gradient of a scalar function V. Real-world examples, just to wrap up here. A static electric field in a charge-free region is considered solenoidal and irrotational. A static electric field in a charged region is irrotational but not solenoidal, right? Because if you have charges in there, then you have sources and sinks, so it can't be solenoidal. A steady magnetic field in a current-carrying conductor is solenoidal but not irrotational. Magnetic fields look like this. You have a bar magnet and you have the north and south end. And so the magnetic field rotates around like this from north to south. And so magnetic fields tend to be rotational. Steady magnetic field in a current-carrying conductor, it's not irrotational. Neither solenoidal or irrotational is an electric field in a charged medium with a time-varying magnetic field. So we haven't gotten into time-varying stuff yet, but that's an example there. And conservative, as I mentioned, static electric fields are conservative because they can be expressed as the gradient of another function called the electrostatic potential. So we'll get into that when we talk about electrostatics. So just in summary, we've covered a lot of ground in this module. This is just a chart that summarizes some of the vector operators and the divergence and Stokes theorem. But we've covered a lot of ground in this module. We've talked about vector addition and subtraction. We talked about the scalar, dot, and cross product, 3 types of vector multiplications. We talked about components and projections. We talked about 3 vector operators, the gradient, which is how quickly a field changes. It's about how quickly a field changes. The divergence is how much a field goes away that diverges outwards or inwards at a given point. The curl is how much a field rotates. We talked about the 3 coordinate systems, Cartesian, cylindrical, and spherical coordinate systems. We talked about double and triple integrals in scalar fields. And then we talked about line integrals and surface integrals in vector fields. And when we talk about surface integrals, it's related to the divergence theorem. It's a way to calculate the net outward flux from a closed surface. The Stokes theorem is a way to calculate the circulation of a closed contour, and that can be calculated using the surface integral of a curl or line integral of the contour going around the contour. And then we just discussed a few ways to classify vector fields. All right, so that will be the end of this module. Are there any questions? Any questions? Okay. All right, thanks everyone for staying a few extra minutes today. I did want to make sure that we finish up this module. So good luck on the homework. It's going to be due tomorrow at by noon. You can submit it online doing a file submission, and then I'll have the grader printed out. And then I will post the solutions tomorrow so that you can study for your exam. Bring questions for the exam on Monday, for sure. Go over as many of the practice problems, go over the solutions, and if you have any questions at all, go ask me on Monday, and we'll do a little bit of a review session on Monday and also start getting into some of the electrostatics, which is the next module. All right? All right, so thanks again for staying extra. I can see a few of you have stayed throughout, so I appreciate that. And I will see you all on Monday. Good luck on the homework. Email me if you have any questions.